Okay. So first, let's address quiz 7 and 8. Several students across both my sections had a lot of questions. So let's bring up quiz 7 first. Oh, before I bring it up, the sequential circuits, right? Sequential circuits. So those. Okay. All right. So first up, let me state that sequential circuits, since we assessed it so recently, will not be part of the final exam. Okay. So chapter 5 was an overview. So chapter 5 is, it's not assessed anyway. Chapter 4, first half is introduction to the binary number system, digital systems like binary numbers, hex numbers, decimals, conversion from binary to decimal, and vice versa, hexadecimal to decimal and binary. Then the theory, the ones complement, twos complement, logic gates, and application of those logic gates to solve a combination, meaning combinational logic circuit. And that's it. Flip-flops, counters, registers, memory is not going to be assessed in the final exam. Okay. So y'all can relax about that. All right. Quiz 7 was about combinational logic circuit, right? So I had binary numbers, binary number system, hex numbers in there, and I asked you to perform a mathematical operation on it, right? So I decided to see what students have learned and how they're thinking, how they're going to approach a problem, something they might not have seen before. Okay, so that was the thinking behind asking question number 3, which is implement the above function with gates. Looked at the quiz responses. I think pretty much everybody was correct about the first, the second, and the fourth. Right? The general feeling was you were able to do question number 1, question number 2, and question number 4. Question number 3, implemented with logic gates, was the one where most students had issues. And it was not so much as a trick as I just wanted to see how students would. So this is a situation where you'd encounter in real life. You study education for 4 or 5 years, then everything that you do as an engineer would be something new. How would you approach something new? Right? This is not completely new. I mean, you're based on logic. You take the ones complement, then you find the twos complement, then you add it to the input, right? You add it to the input or the first number to determine the result of that subtraction, right? So the question was about subtraction. So everybody pretty much did well, well enough on the theory. Theoretical calculation was fine. First step was representing the hex number as binary numbers. So if it's a hex digit requires 4 bits or 4 binary numbers to represent it, meaning 4 wires. So if it's a 2-digit hex, you require 4 bits or 4 wires, right? Each bit can be 0 or 1, 0 or plus 5 volts, right? We can describe hex 0 through F using those 4 wires. 0, 0, 0, 0, all the way up to 1, 1, 1, 1. So far, so good. I think everybody pretty much was okay with that. So we need 2 of those 8 wires. To perform a ones complement, we need a NOT gate. So we feed those wires into a NOT gate, and we obtain the ones complement. Yes. That's what it is. A NOT gate is an inverter. Yeah. So it's just sometimes we have different words for like different things. So yeah, inverter, NOT gate. It's the same term. I mean, not different terminology, but it means the same thing. Inverter. Yeah. But are you referring to an inverting op-amp amplifier? Is that what you're referring to? No, just an inverter gate. Yeah, that's what it is, inverter. Yeah. And we can implement that inverter or not gate using diodes, as we saw. Sorry, not diodes. BJTs, MOSFETs, any kind of logic. Yeah. So yeah, that's one's complement. Then what do we do for a two's complement? We add +1 to the least significant bit, right? That's the two's complement. Right? So least significant bit is here. And you feed it to an OR gate. One input of the OR gate is connected to +5 volts, meaning we're adding 1 to the least significant bit. So two's complement. Right? Thus far, the logic makes sense. And you have done this in the lab too. So for everyone who's taking the lab, I think pretty much everyone does take the lab. When you created those circuits, there were many of the pins that you connected to +5 volts or you connected it to ground. If you connected it to +5 volts, you're applying logic 1. You're applying logic 1 to those pins. If you connected it to ground, you're applying logic 0 to those pins. Okay, so that's how you would apply A1. So if you connect one pin of the OR gate to +5 volts, you're applying logic 1 and adding it the least significant bit. And then you simply want to add the first input, the numbers that are coming in, and you want to add it to the two's complement. So you place an OR gate right there. So you get subtraction. And that's where pretty much most students had issues. And so that's where the kind of twist is. I just wanted to see what students would think. Okay. And that's why it only had 5 points, not more than that. So those 5 points were kind of like extra credit. If you attempted and you did something, you get the full 5 points. So yes. It's a very good point. So if you connect a +1 to an OR gate, wouldn't the output always stay high? And that's where the issue is. So I remember in the class, somebody asked about using an XOR gate. And I was kind of like grinning. I don't know whether it was this section or the previous section. But my guess is they searched online and they found the circuit that is required to do that. So anyway, decimal 1 + 1 is 2. Binary, it would be 0, 1, 0, 1, right? Let me like zoom in a bit. So decimal 1 plus decimal 1 is 2. In binary, it would be 0, 1 plus 0, 1. And the answer should be 1 and 0, right? So if you add 1 plus 1 in binary, the answer is 0. That is known as the sum. And then there is an extra bit that is carried over that is known as 1. I mean, the extra 1 is carried over. So it's known as the carry bit. And so if you want an actual digital implementation of a adder circuit, we need to account for that carry bit. That carry bit is carried over. So you have the sum, and the carry bit is carried over to the left, all these individual bits right there. And the circuit that performs this is known as an adder circuit. Okay, it's an adder circuit. So hence, this is not something I was expecting any student to answer. I just wanted to see what students were going to do. So to implement this logic circuit would be very, very hard, even for an EE student, EE or CPE student also. Okay, so I would not expect anyone from 321 to do it. As I said, I just wanted to see how students would react or do when faced with something new. So yes, you can do one's complement. One's complement can be done easily. Two's complement would require actually having or implemented a adder circuit that would carry on. Okay. So those 5 points are part of the problem, but it's going to be as an extra credit. Obviously, I couldn't state that on the quiz itself. You can do an online search and you can look up a 1-bit or a 2-bit adder circuit. It's implemented with at least 4 different kinds of gates. Okay, so like 2 XOR gates and 2 OR gates to account for the carry bit, for the sum and the carry bit. And so once you have the carry bit, it carries over. Right, it carries over to the left. So 1 plus 1, if you have this kind of hex number that is shown here, and you add 1 to obtain the 2's complement, you have a 0 here, then a 1 is carried over. 1 plus 1 will give you a 0 again, carried over 1 again, which is 0 and 1. So you get a 0, 0, 0, 0. Okay. All right, questions? So that was quiz 7, problem number 3. Obviously, I'm not going to ask anything like that in the final exam. So the final exam would be something similar to the binary numbers, hexadecimal, and I'll go over the final exam just as soon as we're done with this quiz 7 and 8. And then implementing a function using different kinds of gates. Okay. So, which I think everybody was okay doing that too. Now, quiz 8, again, there was a timing diagram question, sequential logic. First question was, let's see. This circuit can be, there were 4 different options. And I think I mentioned this in class where I was reviewing this circuit. What are the possible choices or the possible answers? All of them. I think I stated this in class itself. You can use the circuit for serial input and serial output, or parallel input, parallel output, or any combination. So I think pretty much there's a 100% correct response rate on this one. All of them. So you can use it as all. When clear is 0 and clear is 1, and then enable is 0 and enable is 1. Well, it's clear, preset, enable, any kind of control that is provided for the entire circuit. Either check for the presence or absence of a bubble. If there's a bubble in there, it indicates negative triggering. If there's no bubble, it means positive triggering. Meaning if a bubble is present, which is like a, as a reminder, bubble is a tiny 0 or tiny O. That means it requires a logic 0 to work. If it's not present, it requires a logic 1. So if clear is 0, output is same, does not change. Or output is previous state, does not change. Any combination of those words receive the full credit. When clear is 1, when clear is 1, it is active, so output is equal to 0. Clear means clears out all the data. Output is set to 0. Preset going to 1 means output is equal to 1. So if enable is 0, output is same, output does not change, output is previous state. Again, any one of those or any combination that conveys that is the correct answer. When enable is 1, output is the input. Okay, when enable is 1, output is basically the input. Yes. Just the parallel. because enable only applies to the top. All right, then there was a timing diagram. So in the timing diagram, you can assume, not assume, but you can display, again, see, circuit can be any of the combinations, right? So inputs going in parallel because we are studying A, B, C, D. So if you're studying A, B, C, D, inputs are all going parallel. That's part of the understanding, right? If you look at the circuit diagram, A, B, C, D is at the top going into the circuit. So it's going in parallel. That means it's being used in parallel input. Output is not stated. Output can be parallel or in serial, but parallel is easier. So we simply take parallel outputs. So if I wish to draw a standard clock input, here's a standard clock input for like 5 cycles, 10 cycles, obviously, meaning going on for 10 cycles. No bubble, and it's edge triggered, meaning it's positive edge triggered. So every time a positive edge arrives, input's going to move to the output. Okay. If I'm talking about parallel input, there's 3 sets of input, A, B, C, D. Sorry, four bits input and 3 states, 3 possible states. You can draw it all of them separately, or you can state they are sent one by one into the shift register starting from the top. So I can either start from the left or I can start from the right. I can say, starting from the left, this is the third input, third combination, right? 0, 0, 0, 1. So A is 0, B is 0, C is 0, D is 1. That's the third one. That's the third input. Then I'm going to draw the second one, which is 0, 1, 1, 0. So this is the third, second, and this is the first. And I'm feeding that as input into my shift register. So if I was to draw a timing diagram, I could make this to the left of 0. Or I could draw a separate timing diagram for everything. Okay. So let's draw it like this. This is T and it's going as input. And this is 0. So you start from there. Okay. When the positive edge arrives, the input moves towards the output. Okay. So Q0, Q1, Q2, Q3 would simply take on the values of whatever your input is. It's a D flip-flop. D flip-flop means as soon as the clock signal arrives, it simply moves the input to the output. That's all. Okay. And again, this problem was also more to see how students would think and present. So there are concepts like clock input. Everybody should be familiar with the clock input, right? So that was pretty straightforward. The short answer questions also I thought were straightforward. But after that, it requires students to think a little bit on how they would present their data. So there are multiple ways to present this. You could present it in parallel, as I've shown here. You could also present it in serially, as we saw in the class slide. Both of them, you would receive full credit. So will not be any penalty for that. Okay, so there is no single way of depicting what the timing diagram would look like. Yes. Not at all. So the question being asked is, what if we flip? If the input's being shown this way, that is also fine. You can show 3, 2, 1. You can show 1, 2, 3. It's fine. If you want everything on the same graph and synchronized, then yes, we would show that it's coming from the left. Because if it's coming from the left, then the first state comes first. Then the first state moves on the line, the second one comes in, second one moves on, and the third one comes in. Right? In the circuit, it's coming from the top. So you get the first one, the first clock cycle, the first state moves in, the second clock cycle, the second one moves in, and the third one moves in. A timing diagram, if you show it separately, then it's fine. But if it's all on the same diagram, then requires a bit of thinking. But again, this is not going to be assessed separately on the final exam. Okay, this is just to show students something that they might encounter as an engineer. All right, let's look at what's going to be on the final exam. So first of all, on the final exam page, this has been there on the Canvas site since the first day of class. Okay, make sure you read everything on this page. Final exam is mandatory. It's not optional. It's worth 25% of your overall grade. Having said that, feel free to skip the final exam. Your grade simply drops down to like 75%, right? So you get 0 for those 25%. So, I mean, I can't force you to be here if you don't want to be here. So if a student is happy, if they obtain 100% on everything else, homework, the quizzes, and everything else, they have 100%. The maximum possible grade with that would be about 75%, which is like a C. With extra credit and all, might push it to C+, but I doubt it. So if you're happy with that, then you don't need to show up for the final exam. If you want to get anything above that, 75%, then you do need to take the final. All right. There is no Zoom option. All final exams are in person. I will check IDs for everyone. The reason is because there are several students who are online for the entire quarter. And so while I know most of the students who arrive in person also are in my lab, I can put a name to pretty much every face in classroom. But for those of you who are online, I have no idea who they are. So I would check the IDs for those students. But if I'm checking the ID for one student, I have to check it for everybody. Right? Same rules have to apply. So I will be checking IDs for everyone. Cal Poly ID, driver's license, anything is fine. Our exam is on, when is it on? It's on the Wednesday. Right here, Wednesday from 1 to 4, right here in this classroom. Okay, this is all designed by the Cal Poly scheduling department. Okay, where the classrooms, which courses go into which classrooms, and then the final exam schedule is also decided by them, so that there are no clashes. Meaning this classroom is available to us on a Wednesday from 1 to 4 p.m. That's how it's decided. So that's the official university mandated time, date and time. Okay. Now, if you don't want to take the exam on a Wednesday, you want to take it on the Monday or the Friday or the Saturday before finals week, you have that option. So there are 4 options what students can take. Exam will be very similar. It's not taking it earlier or later is not going to make it easier or harder. Okay, they'll be same level complexity. If you want to take it on a Saturday, it's in a different room. It's in building 20. If you want to take it on a Monday or a Friday, it's in this room. If you're taking it on a Saturday or Monday or Friday, you need to let me know via this form. Several students have already submitted this form. Again, this form, some students submitted on the first day of class itself. Okay, only submit this form if you wish an alternative time. If you're going to show up on a Wednesday, you don't need to submit this form. All right, so all alternative requests, alternative time requests for Saturday will be approved. If the entire class wants to take it on a Saturday, I have enough space in building 20 and I can open multiple rooms. So students can take it anytime. All of the students can take it on Saturday if they want to. Typically about 20% of the students in the class decide to take it on a Saturday. And that creates empty seats on the Monday, Wednesday, and Friday. Okay. So Monday and Friday, depending on how many seats are available, I can approve those student requests. First come, first serve. All right. So think over it and let me know via this form. Final exams are all open book, open notes. You can Bring your electronic devices, tablets, laptops, but they're restricted to course material. Internet access for course material is fine, but not for anything else. Meaning you can look up the class notebook, you can look up the Mastering Engineering website for homework and homework solutions, quizzes, slides, all of that is fine, but not going online. As an example, you perform the ones complement, the twos complement, and you perform the subtraction. So you did a binary. You can do a decimal to binary conversion, binary to decimal conversion. You can perform the math, but you can't go on the internet and verify your answer by going to an online calculator. Okay, as an example, to show me the work, you can't verify your answers. For the other problems, you can search all you want. You won't be able to find the answers. So again, no dial-a-friend or anything like that. So yeah, laptops, tablets are fine. I'll be in the back. You can be as close to the power outlets as you want. There are power outlets along the wall over there, along this side. This is on the back of the wall, the front right here. Obviously, I can't stand here and monitor everybody's laptops or tablets, so I'll be pretty much in the back. Then okay, let's see. Again, read everything on this page. Okay, you have had the entire quarter to read it, but if you haven't yet done so, please go ahead and do so. Let's look at chapter 1. All right, so every chapter there'll be some fundamental questions, short answer questions based on fundamentals and the concepts. Okay, so same for chapters 1, 2, 3, and 4. Okay, chapter 5 is not going to be on the final exam. The latter portion of chapter 4, which is sequential circuits, is also not going to be on the final exam. All right, diodes. Circuit analysis is something we did at the beginning, but again, it's not going to be assessed separately. At this point, I would have to assume pretty much everybody should be familiar with the basics of circuit analysis. So I'm not going to assess it separately. Fundamentals and concepts about semiconductors, how are P and N-type materials created, how a PN junction diode is created, how it works in forward bias, reverse bias. What do those terms mean? And then load line analysis, right? Load line analysis, you should be familiar with that. Ideal diode model, pretty much a guarantee. Ideal diode model is used throughout the chapter, right? Whether it's for just analyzing diode circuits or analyzing Zener diode circuits or analyzing clipper circuits or clipping circuits, ideal diode model is used for everything, including rectifier circuits also, right? So please ensure that you read up ideal diode model and solve the examples, the homeworks, and the quizzes. Ideal diode model, you make an assumption based on whether the anode is higher than the cathode or not. If the anode is higher than the cathode, it's forward bias, and your assumption would be that the diode is on. You replace it with a short circuit, right? If the anode is lower than the cathode, diode is off. You replace it with an open circuit. Because it's an open circuit, voltage across it should be negative and current should be equal to 0. So you make an assumption. Based on the assumption, you replace the diode with either a short circuit or an open circuit. If you replace it with a short circuit, voltage across it should be 0 volts. The current should be positive, right? Diode current is measured as going from anode towards the cathode or through the cathode. And so ID must be positive. If it's negative, or if VD is some other value, then your answer is incorrect. If it's reverse bias, then VD must be negative and current should be equal to 0. No current can flow through, right? It's reverse bias, meaning VD should be negative. So you make an assumption and see if your assumption is correct or not. Then we had a problem where we had 2 diodes, and we solve those. Depending on the number of diodes, if you have n number of diodes in a problem or in a circuit, then you have n 2 raised to n possible states. So 2 raised to n possible states. If you have 3 diodes, 8 possible combinations, 4 diodes, 16 possible combinations. Then we have the offset diode model. Offset diode model is exactly the same as the ideal diode model, except that the difference is in the offset diode model, in the forward bias, we replace the diode with a voltage source of 0.6 or 0.7 volts. And the problem statement I will have assume 0.6 or assume 0.7. So again, offset diode model is a constant voltage source of 0.6 or 0.7 volts in the forward bias. In reverse bias, it's off. It's an open circuit. It doesn't change. Okay, ideal diode and offset diode are exactly the same, except in a forward bias, you have a voltage source of 0.6 volts. Shockley equation, voltage terminology for the rectifier circuits. We analyze the rectifier circuits again based on the ideal diode model. Okay, so everything we did here is based on the ideal diode model. And then with the Zener diode, Zener characteristics, Zener voltage regulator, will not do Zener load line analysis. Okay, so I won't assess that. Whatever problem you see in the exam would be more likely than not based on the voltage regulator, Zener voltage regulator. Okay, no load line analysis of Zener diodes. Okay, Zener regulator will load. And then here are clipper and clamper circuits. So diode clippers, again, diode clipper also was analyzed using the ideal diode model. So again, everybody should be familiar with that or become familiar with that. Zener diode clipper, simply adding Zeners on with the regular diodes, and will not assess diode clampers. So no clamping circuits. Okay. And that's the end for chapter 1. Chapter 2 was BJT. Again, from the chapter, it's device physics, fundamentals, concepts, short answer questions. Right. And then fundamental equations that govern the BJT. Operating modes, cutoff, saturation, and active, determination of the operating mode. And determination of the operating mode. And we did a couple of examples regarding that. So to determine the operating mode, look at the voltages, base emitter voltage, and then look at VCE. And then there was load line analysis. So please ensure that you're familiar with BJT, common emitter load line analysis. And then we did a problem showing how we can use it as an amplifier. So again, please review this problem. Okay. For resistor bias, not going to assess separately, just part of the circuit. So if you have a circuit, you're analyzing it, you're determining the voltages at the terminals. So not going to be assessed separately. And also keep in mind, PNP transistors, everything is the same for PNP as it is for NPN, except the holes and the electrons are switched, right? Holes and electrons are switched. So the voltage polarities are flipped and the current directions are reversed. NPN transistor, current comes out of the emitter like this, hence the arrow points out. PNP transistor, current is flowing into the emitter, hence the arrow points in. Okay, so everything remains the same. The operation remains the same. Everything else remains the same. Physical construction is the same. The only thing is holes are switched for electrons. Electrons are switched for holes. All right, then we had chapter 3, op-amps. Op-amps, again, fundamentals, concepts, inverting, non-inverting amplifiers, summing amplifiers, and that's it. Let's stick with the homework and the quizzes and the in-class solved problems, and you should be good, okay? No active filters. So at the end, we had active filters. So no filters. Pretty much just homework, quizzes, and in-class solved problems. Yes.
The difficulty level, would you say?
Kind of. So yeah, let me say that, yes. So the question being asked is the difficulty level going to be similar to the Monday quizzes? I wouldn't put sequential in there. Not sequential is not going to be assessed anyway. And that's more of long questions. I don't know about long. Typically students, the earliest the students start leaving is like an hour and a half, 2 hours. Average would be between 2 to 2.5 hours. And some students like to say the entire 2 hours, 50 minutes. But I would say about. Oh, short answer questions or something like that. Yeah. So I will have that. Yes. Yeah. There will be short answer questions based on fundamentals and concepts. Yes. All right. And then chapter 4, already covered that all the way up to, so we started with binary number system. Right. Binary to decimal, decimal to binary, hexadecimal to binary, binary to hexadecimal. All of that, make sure you review gates and implementation of a combination of gates, which is what we did in this last quiz. I mean, the previous quiz. And that's it. We'll end there. Combination logic. Nothing beyond that. No flip-flops, no registers, no counters, nothing. We just assessed that recently, so not going to be part of the final exam. All right, and that's it. That's it for the final exam. No class on Friday. Friday is just open office hours. I'll be in my office. So you can show up anytime between 9 to 12. I mean, 9 to, first is 9 to 10, there's 11. So all the way from 9, let's just say pretty much all day. I should be in the office. Okay. Should be in the office. I'll also be available through finals week. I'll be on campus pretty much every day. So I have a couple of workshops and conferences on Monday and Tuesday, but I'll be here. So if you have questions, send me an email, stop by my office. Just check before coming. All right. Okay, thank you very much for the quarter. One final thing is course evaluations. So I'll recall I stated on the first day of class, I went over this. Basically, this is a little bit of extra work that we ask students to do. And so in response, as a favor, because you're doing extra work, I like to offer extra credit in the amount of the response rate. Right now, the response rate is about 11 students of 38. Right. So the only thing we see is basically the numbers. And Friday is the deadline. So 11 of 38 is, well, it's about 30, I would say less than 30%. So every student in the class receives 0.3 points towards their overall grade. So if you end up with an 89.7, that bumps you up to a 90. Okay, so it applies directly to your overall grade. So whether a student participates or not, they still receive the credit or the benefit. Okay, these are important to us. We review them individually Our department committee reviews it. Then the chair of the department reviews it, and the dean also reviews it. Okay, and it forms part of our official file. It stays on there forever. So again, it's important to us. Please describe your experiences in the class. Constructive criticism is always welcome. We need feedback so that we know what we need to do, better. And which also had the unofficial evaluations throughout the quarter. So I have those two. I will tally those up. That's also worth extra points. So one more thing about that I always like to point out is that the scale is from 1 to 5. 3 is in the middle, but 3 is not neutral. So 3 is not average, it's not neutral, in the same way that 50%, if you earn a 50% in any class, it's not in neutral grade, it's not an average grade. 50% is a F, failing grade. So in that same similar scale, 3 is not neutral or average. And the only reason I bring this up is because some few quarters ago, I did receive a feedback where it says I'm going to choose 3 because it's average or neutral, something like that. And so that's when I realized that everybody may not be familiar with the scale. So I always like to point that out. And having said that, obviously, every student should choose what describes their experience the best in the classroom. Okay, whatever fits your experience, that's what you say. All right. So I would bid you a good day, and I will see you all, well, either Friday or Saturday or sometime in finals week. All right. Thank you all.